Welcome back. Today we're in lesson 4 of Algebra 2, and today we're going to review the distributive property, got ahead of myself, solutions of equations, and the change sides, change signs mantra, which is really not, but we will review it anyway, just to explain what that means. So the distributive property is a property of real numbers that permits two approaches to the simplification of expressions such as, when we say 3 times 4 plus 5. The first approach is to add these two together and multiply it by 3, which we know would be 27 because 4 plus 9 is 9. 4 plus 5 is 9. 3 times 9 is 27. But we could also solve this problem like this. We could say 3 times 4 is 12. Plus 3 times 5 is 15, which would still give us 27. So we have the original form, which is PEMDAS, to do everything in the parentheses first and then multiply, or we could use the distributive property, which supersedes PEMDAS, and just apply the multiplication to whatever's in the parentheses first. So we have those options. All right, I'm going to clear this out. We know this. We know how this works. Y'all remember it from last year. It wasn't too long ago. Let's jump into example 4.1. So we have a problem. I'm going to pause the video, write it down, and let it magically appear before your eyes. All right, and here's our problem for 4.1. This is a standard problem from distribution. We know that we have to take this fraction and multiply it by this fraction, and then by this fraction, and then combine any like terms that result. Factor anything out that we can, and simplify it as much as possible. So, for the sake of remembering, I'm going to allow you guys to work this problem. So pause the video, write this down, solve the problem, and then press play and see how much you remember. Alright, if you finish solving the problem, then you should have gotten 4 over a squared b3 b cubed minus 12a. Now if you got 4 negative a or 4a negative 2 b negative 3 minus 12a, that is correct as well. It's just not with all positive exponents, which I did not tell you to do, but that is the correct answer. So this is just the precursor to the final answer. All right, so if you got that correct, good job. If you did not get that correct, then let's walk through it. We got 4a squared over b times the first fraction, which is b, to the negative 2 over a to the 4. So we multiply those together, which gives us 4a squared, and you just write what you have on the top. 4a squared b negative 2, that's everything across the top. And then we brought our b to the top, which means we flipped the exponent, so it became a negative 1. Same thing for the a. We flipped the exponent, it became a negative 4. Same thing over here. We said 4a squared over b times, which is this, times this, 3ba over a squared. So 4 times 3, we multiplied our constants. So that's going to be a negative 12. And then we had a squared, b and a across the top. And then we had a b to the 1, so when we brought it to the top, it became b to the negative 1, times a squared. When we brought it to the top, it became a negative squared. So we just combined our base variables and exponents because we had a squared and a to the negative 4. That became a to the negative 2. We had a b negative 2 and b negative 1, so that became b negative 3. Over here we had an a to the 2 and an a to the negative 2. 2 minus 2 is 0. Those canceled each other out, but we had an a left, an a to the 1. And remember, you can stick your 1s over the tops of the single or the no exponent variables to help you with your math. So we had an a to the 1, and then we had a b to the 1 and a b to the negative 1. 1 minus 1 is 0, so no b's left. So all we had was 12a over here. And then just to make all of our exponents positive, we flipped the negatives back down to the denominator and made them positive exponents. So our answer is 4 over a squared b cubed minus 12a, and that's our final response. All right, if you got that, congratulations, you remember well what we did last year. Let's move on to example 4.2. Let me clear this page. All right, let's, I'm gonna pause and write it down. All right, I have written down the problem. We can work this one together so you can kind of see, for those of you who weren't in my class last year, how I do things. So right away we see that we have a b to the 0. That's 1. Any exponent constant with a, any variable or constant with the exponent of 0, that means 1. So we just cross it out, because anything times 1, we know there's an invisible 1 here. It's just included, right? 1 times this times 1, the 1's cancel each other out. So you just mark it out. You ignore it. It's just something to clutter up your page. So get rid of it. So it leaves us with a to the negative 3 over c times all of this. So we're just going to write it out. Do the top first, and that's times the second fraction. And then you have the next, the bottom, times the first fraction. Now we're going to do the second fraction, and it's whatever's on top. Now you do whatever's on the bottom. Now let's bring everything to the top, written in the order it's written. This becomes a negative 1. This becomes a negative 2 because we flipped it up. And now we want to bring our constant to the front because we put constants in the front. That's the way we do. This becomes a negative 1. Because we're flipping this to the top, we do the opposite sign. So it becomes a positive 2. Okay? It was already a negative 2. Right now we just combine our exponents and bases, or our exponents with like bases. So we have two a's. We have a negative 3 and a positive 2. So it's going to be a negative 1. All right, this is a 1, this is a 1. We only have one b, so we just write the b here. Now we have a c, positive 1, negative 1. So let's cancel each other out. So that leaves us with a c, negative 2. Now we could do the next term. We have a 3 as a constant. We have a negative 3, a negative 2. That becomes a negative 5. And then we have c, negative 1, and a b, positive 2. Now we can flip them down into our positives and negatives. And so we would have b over a c2 minus 3b2 over a5c. And that would be our final result. Okay? And that's if you want all of your exponents positive. That would be the result that you have. All right. Let's move on to solutions of equations. If you need any help with this right here, I am more than happy to send me a message. Let me clear the page. We're going to talk about, like I said, solutions of equations. We can add the same number to both sides of an equation without changing the truth or the falsity of the equation. So what that means, it goes back to our rule: whatever you do to one side, you have to do to the other side. So if we had 4 plus 3 equals 7, we know this is a true statement because 4 and 3 are 7. But if we subtracted 3 from this side, we would need to subtract 3 from this side. That would leave 4 here and 4 here. Still true statements. If we multiply this side by 2, we would need to multiply this side by 2. That would give us 8 equals 8. Still true statements. Still equivalent on both sides, which makes this equal a true statement for this math. So that's what leads us to understand that x plus 3 equals, or x plus 7 equals 10, that we can subtract from both sides and find the solution for x. This logic is what leads us to this logic. All right? That is all we have on solutions of equations. We're finding the truth of x by keeping the statement balanced. Whatever we do to one side, we do to the other side. All right? Now that leads us to what we call equivalent equations. If I were to give you a problem, let's say x plus 10, or x plus 7 equals 10, the same one we had up here, and then I had 4 plus x equals 7. If we solve this, we know that x equals 3 over here, and x would equal 3 over here. Even though it's not the same equation, the solution is the same. And because the solution is the same, this is what we call equivalent equations. And this is your example for that. So make sure you write this down in your notebook. This is the an example or a sample problem of equivalent equations. You just have to have the same solution and they become equivalent. Excuse me. Got a bug in my throat or something. I don't know. All right, so we know we can use the addition rule for equations, which is you can add or subtract the same quantity. We discussed that up here, and it keeps it true to both sides. Or you can multiply or divide both sides by the same number, and you get a true statement. If we had divided both sides by 2, then we would have had 2 equals 2. As long as we do the same thing to both sides, then we can do that. We can do whatever operation we need to simplify the problem as long as we do it to both sides at the same time. All right, let's move on to our next example problem, example 4.3. I'm going to clear the page. Pause if you need to. And we have, let me write 4.3 up here so you can keep up with your notes. All right, this is in parentheses. This is minus. All right, so we have this problem here. We know we need to do what's in the parentheses first, right? Can't really do anything here. We know we have 12 minus. Let me write that a little bit better. There we go. Now you can see that a little bit better, and I have a little bit more room. Whenever you have a negative symbol in front of a parenthesis, sometimes it helps to envision that 1 because you're asking for the opposite of everything in this parenthesis. So let's go ahead and do as much as we can do on this side before we start balancing them out. So we have 12, negative 1 times 2x is going to be a negative 2x. Negative 1 times positive 5 is going to be negative 5. Now we can move on to this side. We have negative 2. We can't really do anything in here, right? And this is just addition. You could still do the same thing here, but there's no point. A positive times whatever is not going to change anything. It's the negative that changes the sign. So you can leave it as it is. All right. Now we can start combining. We have 12, which is a constant, minus 5. That's going to give us a positive 7 minus 2x. And we have a negative 2 and a negative 5. So it's going to give us a negative 3. So it's going to give us negative 5 plus x. All right, so if we want to see what we got here, I like to have my x's positive. So I'm going to put the x over here. I'm going to add 2x to both sides. And I'm going to add 5 to both sides. Just for the sake of having a positive x. All right, those two cancel. That leaves me with 12 equals, and remember, if you have a variable by itself, that's a 1, so it's 3x. 12 divided by 3, we divide both sides by 3. This cancels here. This is 4, so the answer is x equals 4. If that's what you got, then very good. You understand and you remember. So let's do 4.4. It's another of the same thing. Remember, as we do these problems, you need to be writing them down so that you have an example in your notes of what we're doing. So you can go back and look at your example. If you get stuck and don't remember how to solve a problem, you go back and say, well, what did we do in the lesson? And then that will show you how to work it out. Here's another one. Pretty good size problem. It's mostly fractions. Yay! Like fractions, actually. Fractions they're okay. Nothing special. They just are what they are. All right, let me make sure I wrote that down correctly. Yes, that's what we have. All right, so first let's do our distribution. Let's get rid of these parentheses. So 3 times, whenever you have a whole number, remember we just put it over 1. Now it becomes a fraction times a fraction. Easier to do. So 3 times 5, that's going to be 15 over 6 minus 15 over 3x equals, now this is, put your 1 here, right, over 1. Negative 1 times negative 1, that's going to be a positive 1/2, right? And a negative 1 times x is going to be a negative x. All right, so now we can solve. We see we have 15 over 6. We can't reduce that to a whole number, so let's just leave it as it is. This we can reduce to a whole number. Let's bring our x over here because I like positive x's, which means we'll bring our 1/2 over here. All right, I'm writing too big. I need to write smaller. So that gives us, let's see, that's going to give us 15 over 6 minus 3 over 6. So 15 minus 3, that's going to be 12 over 6 equals 4x. 12 over 6 is 2. So let's go over here and say 2 equals 4x. So we divide both sides by 4. Then x is equal to half. And that's our final answer. Now on your notebook paper, I expect you to keep continuing down the sheet, not going over to the right like this, but this will be the next line and this will be the next line. All right. All right. Now we're going to talk about the change signs, change sides, change signs. And basically, it's just a shortcut so you don't have to do this step right here. It's the same thing that we've been doing all along. It just is a method of writing it out where you don't have to do the subtraction. That's all it is. Let's do a problem like that. I'm going to clear the page. So for instance, in example 4.5, I'm going to start small here, and we're going to use the change signs to solve for x. So we have x minus 2 equals 7. So all this is saying is that we can flip this over without having to do subtraction. So we could do x equals 7 plus 2. It is the same thing that we would normally do. Normally we would do x minus 2 equals 7. We would say plus 2 plus 2, x equals 9. All this is saying is you can rewrite it, flip the sign and put it on the other side, and then it is more succinct. So then you can write, it's the same number of steps. Like we have a line here, and a line here, and a line here. This is more illustrative. This is more neat. Okay, so it's the same exact process. Do whichever one works for you. If this is what works for you, so you can see what you're doing, do it. I don't care. This is just another way to do it so that you can have a more neat and free-flowing thought, or a thought you can follow. So we know we flipped from this side over to this side. That's what my son calls it. He calls it the flip-flop. You flip-flop this one over here, you change the sign. Same answer, same answer. Either way works. It's up to you which way you want to do it. Here's another one, 4.6. And we're going to use, we call it transposition. Change sides, change signs is transposition. We're going to solve for p. We have p minus 3x plus 4 equals 7y. Remember, we're solving for p. So I'm going to write, we want to solve for p right here. So all we have to do is take all of this over here, flip the sign, and move it. So p would equal 7y plus 3x minus 4. Now I must say that one is a faster step because this is our answer. Normally we would write plus 3x minus 4, cross them out, and write the same thing over here, and then rewrite it. So this is faster in this instance. We got to p much faster than using this process. Okay. So in this instance, I would say it is a better way to go. Use your best judgment. 4.7. We're going to solve for y. Okay. And we have 3y minus 2x plus 5 equals 0. We're solving for y. So the first thing we're going to do is we're going to move all this over. So we have 3y equals 2x minus 5. Remember, we have to change the signs. Now we divide everything by 3. Y equals 2/3 x minus 5/3. Easy peasy. And that's all we got. So in some ways, when you have variables, this could be faster. Use your best judgment. All you have to know is that when you change this side, you change the sign, because that's what we're doing. We're adding it to this side to get rid of it. But whatever we did one side, we have to do the other side. So that means we add it over here. So it is changing sides, changing signs. So change sides, we change signs. All right, you can write that on here as a way to remember how to do it. It's ultimately this step up here. This is why When you change sides, you change signs. This is your why for why this works. All right, that's all we have for lesson 4. I'll see you in lesson 5.